Today's our topic is the continuation of symmetric and skew symmetric matrix. We have already studied that if A is any square matrix, then A plus A transpose is symmetric and A minus A transpose is skew symmetric. How to prove this is, let C equal to A plus A transpose. To prove that C is symmetric, what you need to prove? You have to take the transpose of C. That means the transpose of A plus A transpose. Now you have to apply the properties of transpose. As you have already studied the properties of transpose, A plus B transpose equal to A transpose plus B transpose. So if you are applying that property, what you get here, the first term you can take transpose, so you'll get A transpose, plus taking the second terms transpose, you get A transpose whole transpose. Again you have learned another property, that is A transpose whole transpose is equal to A. So if you are applying that, the second term will convert to A, and this is again equal to A plus A transpose because of commutative property of addition. So finally what you are getting is, you are getting C again, because C was already defined as A plus A transpose. So I'm writing here as C. So therefore what we got is C transpose equal to C. That implies C is a symmetric matrix. C is a symmetric matrix. Similarly, the other A minus A transpose, which is skew symmetric. To prove that, you take this as B equal to A minus A transpose. Now recollect the definition of skew symmetric matrix. A matrix C is said to be skew symmetric if C transpose equal to C. So this definition you will be applying here to check. We will be applying to check the skew symmetry of the matrix. That means we are taking B transpose and it is a transpose of A minus A transpose. So as we have learned the earlier one, the property of transpose, A plus B transpose or A minus B transpose, it becomes A transpose minus B transpose. So applying the property, what you get here, it is applying the transpose on each term. You get A transpose minus, apply the transpose here. So you will get A transpose whole transpose. Again, by property of transpose, you know that it is equal to A. And if you take one minus outside, what you get is minus A transpose, and you can see that this is nothing but B. So we can write this as B, sorry, minus B. So finally, ultimately what we got, B transpose equal to minus B, that implies B is skew symmetric. K into A, the scalar multiplication of A with a real number K is symmetric if A is symmetric And also we can write K into A is skew symmetric if A is skew symmetric. So keeping this in mind, you can see that if A plus A transpose is symmetric, so half of A plus A transpose is also symmetric. Similarly, half of A minus A transpose is skew symmetric because here we are applying the scalar multiplication. Now, by keeping these two in mind, we can create a very interesting theorem that suppose we are adding these two matrices. So, or you are getting A, or you can write it as A equal to half of A plus A transpose plus half of A minus A transpose. So every square metric you can write like this. And what is the speciality here is the second matrix is skew symmetric. It is skew symmetric. And the first matrix, the first matrix is symmetric. The first matrix is symmetric. So a theorem can be generated from here, that is any square matrix can be written as, can be expressed as sum of a symmetric and a skew symmetric matrix. So what is that is A equal to 1 by 2 A plus A transpose plus 1 by 2 of A minus A transpose. It's a very important one. Now by using this, you can have these type of questions. Suppose A is, or express A as sum of a symmetric and a skew symmetric matrix. Where A is given as 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you are applying this theorem directly, it is very easy to find. So you know that A is equal to half A plus A transpose plus half A minus A transpose. So first we will find out what is A plus A transpose, and then you find A minus A transpose. So we can write here on the right side what is A transpose. A transpose means The first row will become the first column. The second row will become the second column. The third row will become the third column. Now you need to find what is A plus A transpose. Means the matrix addition you have to do. And how to add the two matrices is add the corresponding elements. So we'll get 1 plus 1, that is 2, 2 plus 4, that is 6, 3 plus 7, 3 plus 7, that is 10, 4 plus 2, 6, 5 plus 5, 10, 6 plus 8, 14, then 7 plus 3, 10, 8 plus 6, 14, 9 plus 9, 18. And we actually need to find half of this. So take half of this, means we are just using the scalar multiplication. That means every element you multiply by 2. So this 2 into half, that is 1, 6 into half, 3, then 5, then 3, 5, 7, 5, 7, 9. So that is your half of A plus A transpose. Next, you need to find half of A minus A transpose. That means these matrices which you have written, you have to do the subtraction. The corresponding elements you have to subtract. So we'll get 1 minus 1, which is equal to 0. Then 2 minus 4 minus 2. Then 3 minus 7 minus 4. Then 4 minus 2, 2. Then 5 minus 5, 0. 6 minus 8 minus 2. And now 7 minus 3 is 4. 8 minus 6, that is 2. 9 minus 9, that is 0. So these are the two matrices. The first one is symmetric, the second one is skew symmetric. Now, as per the question, express A as the sum of symmetric and skew symmetric matrix. So this A to be expressed as A is your 1, 2, 3, 4, 5, 6, 7, 8, 9. This to be expressed as sum of a symmetric and a skew symmetric matrix. The symmetric matrix is 1, 3, 5, 3, 5, 7, 3, 5, 7, and 5, 7, 9, which is symmetric. That is with half I am multiplying 0, minus 1, minus 2, then 1, 0, minus 1, then 2, 1, 0. Okay. So this is the one. The first one here it is symmetric. And the second one is skew symmetric.